Okay, so for the complete solution to problem number 2, what we want to do is use the integral version of the center of mass formula. So the integral dm, which means the sum of all of the little dm pieces. Now remember, that long bar can be broken up into little tiny bits. Each little bit is a dm. And what we're going to have to do is add up all of the dm's. So that's the integral dm. And then we're going to multiply that by the x-coordinate of the center of mass. And then that's going to equal the integral of each of those little bits of mass times each one of those masses x-coordinate. So the x-coordinate would be from here to here. That would be the x-coordinate. But usually we don't write dm times x in parentheses like this. Usually it's written the integral of dm x center of mass equals the integral of x times dm, like this. So we're taking the sum of all of the x coordinates times their corresponding dm values. But the convention is not to put the parentheses on that integral. So I'm going to go back and take those parentheses off. And you need to realize that we're taking the sum of these products. So these parentheses are understood, but they don't have to be drawn like that. So there's the formula we want to use. But we don't like to integrate over dm's. We like to integrate over dx's. Each little dm corresponds to a little change in the length of the object. And you can call that dl, but ultimately we're going to call that dx. And that's infinitely small, so each dm corresponds with a change in length, a little dx. So to transform the dm's into dx's, we have to introduce linear mass density. Now you might recall regular density is mass divided by volume. But what we're going to be using is linear mass density, which has the symbol lambda, which is mass divided by length. And if I rearrange this, the mass ends up equaling the linear mass density times the length. So if I multiply the linear mass density times the whole shebang length, I'll get the whole shebang mass. But what if I multiply the linear mass density times a little tiny piece of the length, dl? Well, then I wouldn't get the whole shebang mass. I'll only get a little piece of the mass, dm. So this little dm right here is related to this little change in length, dx, by this formula here. But you can see it's in dl, and we want to change that into dx. So I could rewrite this dx. So a little tiny change in the mass, a little increment of mass is equal to lambda times a little tiny change in x, dx. So this is the substitution I'm going to use to transform these integrals down below. So instead of adding up all of the dm's, I'm going to add up all of the lambda times dx's. And again, I just want to write those parentheses like that to show I'm taking the sum of these products, but convention has it we don't include those parentheses. And then that's going to be multiplied by the x coordinate of the center of mass. And then that equals the integral, right from there, of x, which was just brought down right from there, times, instead of the dm though, I know the dm can be replaced with, up here, lambda times dx. And again, I just want to put those parentheses to say, hey, we're taking the sum of these products. But convention has it, I don't have to put those parentheses there. It's understood. It starts with the integral sign, and it ends with the dx. So I could take those parentheses away. Now, I'm just going to change the order of x and lambda because it's a constant. And if I want, I could actually pull these constants out front. Lambda is just a constant in this problem, so I could pull it out in front of the integral sign. So I have lambda integral dx times the x center of mass equals lambda x dx. And I'm going to be integrating these from 0 to 2 meters, the whole shebang length. And that was given up here. So this is also going to be integrated from 0 to the whole length, which is 2 meters. Now, there's a 1 times the dx, and remember, instead of taking the sum of these products here, what I can do instead is take the antiderivative of what's sandwiched in between the integral sign and the dx. And the antiderivative of 1 would just be x. So it's going to be lambda. There's that lambda right there. But then the antiderivative of 1 is an x. And I'm going to put in the boundary conditions 0 to 2. And that's all going to be multiplied by the x center of mass. Now over here, I have my lambda, which I'm just going to bring down. Oopsie. And again, instead of taking the sum of these products right here, the fundamental law of calculus says, instead of doing that, I could calculate that by finding the antiderivative of what's sandwiched in between the integral sign and the dx. So I'm going to take the antiderivative of this x right here, and that's going to be 1/2 times x to the second power, using the power rule in reverse. And you could check it. If you took the derivative of 1/2 x squared, what would you get? You would get that x right there. And then I have to put in my boundary conditions between 0 and 2. So now I'll come up here. If I put in this 2 right here for x, I'm going to get lambda times 2. And then if I put in the 0 for that x, I would get lambda times 0, which of course is 0, and we could just drop that or not write that to begin with. And all of that is going to be multiplied by the x coordinate of the center of mass. And then that's going to be equal to the right-hand side, which is going to be lambda. And now I put that 2 in for the x. And what do I get? 1/2 2 squared minus, if I put in the 0 for the x, lambda times 1/2 times 0 squared, which is just 0. And if I simplify this equation, I end up getting 2 lambda times the x coordinate of the center of mass equals, this term goes, and here I have a 2 squared, which is 4 times 1/2. So I get 2 lambda again. And then if I divide both sides by 2 lambda, the 2 lambdas cross out, and I get the center of mass is equal to 1 meter, which I knew all along it was going to be right here in the center of the bar. It's a uniformly dense bar going from 0 to 2. Where's the center of mass? Right at the beginning there, right in the middle, I mean. But we wanted to practice using our calculus integral here. There you have it.